course, the last group are stars with the masses above 8 solar masses. Now, once the star is in main sequence stage, it is in state of hydrostatic equilibrium. So regardless of its mass, once the star becomes the main sequence star, it is in hydrostatic equilibrium. So what that means is that the force associated with a gravitational contraction is, and it's trying to squeeze the star, right, to make it smaller, is balanced by the gas pressure everywhere within the star. Okay, so let me try and illustrate this. Okay, this is not quite sphere, but it's at least it's smooth. Okay. So say at this level within the star, the force of gravity is trying to compress the star, but the gas pressure is precisely balancing this force of gravity. So this is the pressure force, and this here is gravity. If I go to the greater depth, the force of gravity, the weight of all those layers above this particular level is going to increase. So the force of gravity is larger the deeper you go. Nevertheless, it is balanced by increased pressure at a greater depth. Okay? So in the state of hydrostatic equilibrium, the force of gravity that is causing the star to contract is balanced by the gas pressure. So that means that as we go deeper into the star, the pressure increases, but the pressure and temperature always go together. The higher pressure is usually caused by higher temperature of the gas. And I mentioned that earlier in 1P01, for instance, if you measure the pressure of the gas in your tires first thing in the morning before you drive your car, it shows a certain value, and then you drive it for a while, and once you reach your destination, you measure the pressure again, and you will notice that it is somewhat higher, depending on how long you drove and how fast, so on and so forth. What is happening, of course, is that there is a friction between the rubber on the tires and the pavement. And that force of friction causes basically, it's a dissipative force, causes the work done by the force of friction is transformed into thermal energy that warms up the air in the tires. So as its temperature goes up, the pressure created by the gas in the tires also goes up. So in normal matter, the pressure and the temperature, they always go together. So how is this hydrostatic equilibrium maintained? It is maintained through so-called pressure temperature thermostat. Okay, so what's happening? Well, suppose that the rate of nuclear fusion reactions in the core increases, so that more energy is produced. As the more energy is produced, the temperature is going to go up in the core, and the pressure follows. Both temperature and pressure increase. Now, this increased pressure will push the top layers out. The star would slightly expand, and as it expands, it cools, which will bring down the temperature and the pressure in the core. And the opposite may happen, that for whatever reason, the rate of nuclear reactions in the core goes down. Less energy is produced, there is less heating, the temperature drops, the pressure drops. The top layers above the core, they now start squeezing the core, it contracts, and this gravitational contraction will increase the temperature of the core, and as a result, the rate of fusion reactions will go up, right? And things will be as usual. And that increased pressure will push out the top layers, and the star would expand, and as a result, it will cool. Okay, and the reaction rate reduces to its steady value. Okay, so there is a nice analogy in your textbook. The same thing happens with the covered pot of boiling water. Okay, so if you have a pot of water and you boil it, trying to cook something, pasta or whatever, but it's covered. There is a lid. As the water evaporates under the lid, the pressure increases and it tilts the lid so that some of the steam is let out. The pressure under the lid drops and then it comes down. More water evaporates, enough pressure builds up, pushes up the lid, right? The steam is let out, the pressure under the lid drops, and it closes. So if you are listening to the sounds produced by a covered pot of boiling water, you hear that clanking sound, right? As the lid comes up every now and then and releases the steam out. Okay, so that's the analogy. That's roughly what the star does. However, it turns out that while on the main sequence, the luminosity of stars, all stars, regardless of their mass, increases slowly over time. For instance, it turns out that our sun is now 30% more luminous than what it was when it was created, when it became a main sequence star about 4.6 billion years ago. And it's quite large. It's indeed of astronomical size. Right now it's about 4 times 10 to the 26 watts. Is 30%, is about 30% higher than what it was when the sun became the main sequence star 4.6 billion years ago. We are roughly now halfway through the sun's life. It's been shining for 4.6 billion years with, as I said, slowly increasing luminosity, so that now it's 30% more luminous than what it was when it became the main sequence star. And it will shine on for another about 4.65 billion years, and eventually all of the hydrogen in its core will be used up, will be all fused, and then the sun will start to die, go through different stages, which are of course much shorter than its main sequence life, and it will fizzle out. And we'll discuss in detail what happens to a star like our sun. And the question is, why is this happening? Why is the luminosity increasing over time? And of course, we can provide an answer using the laws of physics. It turns out that in a gas, the pressure is given by the number of particles per unit volume, so-called particle number density, which is number of nuclei, regardless of their kind, per unit volume, and temperature. That's how the gas in the air in this room behaves. That's how the gas in the star behaves. The pressure is proportional to the number of particles per unit volume and the temperature of the gas. But look, if we take, for instance, proton-proton chain, what happens is that 4 nuclei, 4 protons, 4 nuclei of hydrogen, when everything is said and done, the end result is that these 4 nuclei are fused into 1 nucleus of helium-4, which consists of 2 neutrons and 2 protons. So over time, the number of nuclei per unit volume is constantly decreasing as 4 nuclei get fused into 1, right, in each fusion reaction. But for the star to be stable, the pressure has to remain fixed, right? The pressure at any given depth within the star, it has to stay the same to support the top layers. So the only way I can keep the same pressure with the decreasing number of particles per unit volume is if the temperature goes up. So to keep the same pressure with decreasing density of nuclei, the number of nuclei per unit volume, the only way out is if the temperature goes up. But as the temperature goes up, the rate of fusion reactions increase because it is proportional essentially to the temperature to the power of 4, producing more energy per unit time. And more energy per unit time means that the luminosity increases. So basically what is happening over the life of a star, when it's in main sequence stage, over time, each star is moving slightly up the main sequence, right? Because its luminosity is increasing, right? Therefore, the higher luminosity corresponds to the points that are higher on the main sequence. So each point on the main sequence moves somewhat up. And it turns out that in about 500 million years to 1 billion years, the luminosity of the sun will be such that all of the water on the earth would evaporate. Okay? There will be no oceans, no lakes, no rivers, no nothing. And the life on earth would become impossible. The life as we know it will become impossible. So, you know, people always worry and say, okay, well, you know, the end of the sun is in about 4.6 billion years when it runs out of hydrogen. In the process, as we will discuss in detail, it will swell up in stages, first time roughly to the orbit of Mercury, which is the planet closest to it, at about 40% of the distance between the Earth and the Sun. And then in the final red giant stage, it would swell up in size when it becomes full red giant, roughly to the orbit of Mars, perhaps swallowing the Earth in the process, right? If the distance between the Earth and the Sun doesn't change for some reason that I'll discuss later when we talk about it, then certainly it would engulf the Earth, right? But we don't have to wait that long, 4.6 or so billion years, for the life on Earth to become impossible. Things will get quite hot much sooner, in 500 million to 1 billion years, when the sun will be so luminous that all of the water on Earth would vaporize. Now, in the past, there's one thing. I mentioned that the sun was 30% less luminous when it became a main sequence star than it is now. And when this will happen, the luminosity will go up maybe by 10%, not as much, not as big a change. So you can say, well, if the sun was 30% less luminous in the past, how come we have fossils of living organisms on Earth that are 3 to 3.5 billion years old? There had to be some kind of compensating mechanism to increase the temperature on the Earth in spite of the reduced luminosity of the sun. And one possibility is that when the sun and the planets around it formed, there was initially on terrestrial planets like Earth a period of very intense volcanic activity. All the gases trapped inside the planet were coming up to the surface. And most of those gases, including the water vapor, methane, carbon dioxide, and others, are so-called greenhouse gases. They trapped infrared radiation. And this trapping causes the atmosphere to warm up. So although the sun was less luminous, there was this compensating greenhouse effect produced by volcanic gases that kept temperature high enough for these first forms of life to form on Earth. Okay? Now, it is not clear to me, at least, that there is an equivalent compensating mechanism that will keep the Earth cooler when the sun become more luminous. I can't think of anything that would actually reduce the temperature on the Earth, unless we somehow manage to in some way block the incoming radiation. Okay, but this happens to all main sequence stars regardless of their mass. Okay, so there are different parts of life of a main sequence star like Sun, contracting protostar. Just before it becomes a main sequence star, it goes through periods of instability, producing these so-called bipolar flows that I haven't discussed. Then it will go through the first red giant stage, where it will swell up to about the orbit of Mercury. Then the core will get hot enough so that helium in the core, because all of hydrogen has been converted into helium, will now start fusing into carbon with the production of energy. But that is short-lived. Eventually, all of the helium is burned. The star wasn't massive enough to start fusing heavier elements, heavier than helium, carbon, and so on and so forth. It swells up into the last red giant phase, when it will reach the orbit of Mars. And eventually the pressure that is built in will push out the top layers, forming so-called planetary nebula. And what is left behind is dead core, non-fusing core consisting mostly of hydrogen and some oxygen nuclei.